Hi again, Math 215 students. We're going to have part 2 of this part B in solving linear systems using matrices. You'll remember that at the end of the first half of this, we had arrived at a list of steps to follow to find the solution of any system of linear equations. In this video, we're going to go through this list in detail and illustrate it with a number of examples. This technique is described in section 1.2. I would refer you to your textbook to see more examples of its application, but let's see what we can illustrate as we go through. We're going to start by taking a look at the very first example we looked at in the first video in this series in part A. You'll remember there we were talking about servings of Cap'n Crunch and Yoplait yogurt and letting x1 and x2 be the number of servings we ate of each of those in a day. And what we wanted to do was balance our calories and fat using the right number of servings of each of those. So we had set up two equations in a system there. And what we're going to do now is apply the steps that we saw described there. We're going to go through them step by step. So step 1 is to write the augmented matrix of the system. And we had talked about in the first video, the augmented matrix that goes with this system of equations looks like this. We've just recorded the coefficients from each equation and the right-hand side in a single matrix. And this is where we start in our technique. Now in step 2, what we want to do is row reduce to echelon form, whatever that means. So before we dive too deeply into that step, let's pause to define what echelon form is. So what I have shown here are two examples of matrices. They're not tied to anything we've done before, but they're each written in echelon form, meaning that each of these matrices satisfies these three conditions. If your matrix happens to have a row of zeros, that row has to appear at the bottom of the matrix. So this matrix, for instance, does have a row of all zeros, and it does appear as the very last row in the matrix. This matrix doesn't have a row of zeros, and that's okay. It's just that if it did, we would need it to appear at the very bottom of the matrix. All right, the second condition you need to satisfy is that the positions of leading entries of rows must move to the right for each successive non-zero row. So let's pause to define what we mean by a leading entry. A leading entry is the first non-zero entry in a row. All right, so for instance, in this first row, the first number is not 0, so it will be the leading entry in that first row. In the second row, we have a couple of zeros before we run into a non-zero entry, and a leading entry is the first non-zero entry. So 2 becomes the leading entry for that second row. This 3 becomes the leading entry for the next row. And then the last row of this matrix does not have any leading entries, just because every entry is equal to 0, and we're looking for non-zero entries. Now, I put the leading entries in red here, and you'll notice that as we move from the first row to the second to the third row, the locations of those leading entries seems to shift to the right. And that's what we need to have happen in order for this second condition to hold. The leading entries in the rows has to move from the left to the right. Now in this second example of a matrix in echelon form, you'll see that we do have the leading entries appearing in the first entry of the first row and the second entry of the second row, so that is satisfied as well. The next condition has to deal with zeros. What we need to have is that all entries in a column lying below a row's leading entry are 0. So in other words, as I look at the leading entries, the entries below each of those have to equal 0. So I see that here. Below this 3, I have all the entries equal to 0. Below this 2, I have a bunch of zeros. Below this 3, I have a 0 as well. Now you'll notice that actually we have zeros below the -2 and the -5 as well, even though those aren't leading entries. And that's to be expected, because let's just imagine for a second that we did have a non-zero entry below the -2. What that would end up giving us is a leading entry, actually, in this column. And that leading entry would need to be moved up so that the leading entries move from left to right. And what will happen if you do have your rows ordered correctly, the leading entries will make it so that all of the columns have zeros if the entries lie sort of southwest of these leading entries. Okay, so in this matrix over here, we have just one leading entry with anything below it. It's this entry here. The 1 is the leading entry. We're going to make sure there's a 0 below it. Now you'll notice that this 2 is also a leading entry, and there does happen to be a 0 above it, but we're not talking about that 0. This condition just talks about the entries lying below a row's leading entry. So the second row doesn't have anything below it, so there's nothing to test there. All right, now if these 3 conditions are satisfied, your matrix is in echelon form. So what we want to do is use elementary row operations to take our augmented matrix that we had created in step 1 and use those operations to push this matrix or to transform it into echelon form. How do we do that exactly? And there is more than one way to do this, so be aware of this. There's more than one echelon form possible from any starting matrix. What you will want to do in general, though, is work one column at a time, moving from left to right, to use the elementary row operations to create the zeros where you need to. So in particular, as we move from the left to the right, I do see that 150 is a leading entry in the first row. In order to put my matrix in echelon column, I would need to have a 0 underneath it. And so what we'll do is see what we can do. You'll remember that the elementary row operations we're allowed to use are these 3, the replacing operation, the interchanging, and the multiplying operation. And so what I'm going to do, one thing I could do, is take my matrix here and keep an eye on that leading entry of 150. In order to create a 0 underneath that leading entry, I'm going to multiply that first row by -2 over 150 and add that to the second row, and that will create my new second row. So in other words, I'm doing a replacing step. I'm replacing row 2 by the sum of row 2 and -2 over 150 of the row 1. Now if I kind of imagine what this first row would look like if I did multiply by -2 over 150, you can kind of see how -2 over 150 was chosen. Multiplying 150 by -2 over 150 creates -2 in that first spot. Taking this 150 in the second spot and multiplying by -2 over 150 creates -2 again. And then -2 over 150 times 2,000 will create -4,000 over 150, and that can obviously be simplified if you reduce the fractions. But I'm going to take the -2 and the -2 and the -4,000 over 150 and add those entries to the 2 and the 1 and the 65 in the second row. And that first -2 plus that +2 will create the 0 I'm after, which kind of tells you why I used 2 and 150 there in my multiplication. The -2 in the second column plus the +1 gives us a -1. The -4,000 over 150 simplifies, and when you add that to 65, the result is 115 over 3. Now, as you take a look at the leading entries here, you'll see that we do have it in echelon form. The leading entries move from left to right as you move from the first row to the second, and below the leading entry in column 1, we do have a bunch of 0. We have a 0. Okay, now at this point, we have gotten our matrix in echelon form, and we are supposed to pause to see if there are no solutions to the system. Is it possible that there could be no solutions here? Well, if you think about this in terms of equations, at this point, this second row of the matrix corresponds to the equation minus x2 equals 115 over 3. Now, that's going to tell us what x2 is equal to. We can solve for x2 pretty easily. And then once we know what x2 is, I could substitute for x2 in the first row to find out what x1 is, and I would get a solution. All right, so we're not going to go through the steps there, but if you kind of think through and imagine what would happen, I can believe that we will find a solution to this system. So the bottom line is that we should be able to solve for the second variable. From there, we'll be able to solve for the first variable. So there will be a solution to the system. Even if I don't see exactly what it is just yet, I can tell already that there should be a solution. Right, now in steps 3 and steps 4, I'm going to kind of summarize what they say here. What we'll want to do is continue our row reduction to obtain the reduced echelon form. So we've gotten our matrix in echelon form. There's something called reduced echelon form we need to describe, and we'll do that now. So we'll say that a matrix is written in reduced echelon form if it is in echelon form, and if the leading entry in each non-zero row is 1, and if each leading 1 is the only non-zero entry in its column. Okay, so let's take a look here. Our matrix that we had written already was in echelon form. Is it in reduced echelon form? And the answer is unfortunately not. We need the leading entry in each non-zero row to be 1. So in this first row, we need the leading entry to be 1. And it's not 1, it's 150. And in the second row, this leading entry is -1, it's not 1. We need to make sure that those leading entries are 1. Okay, so what we might do is, first off, just take a look at, and that -1 is almost a 1. And one of our elementary row operations is a multiplication operation. So if I multiply the second row through by -1 and use that as my new row 2, I'll get a -0, or in other words, just 0, minus a -1 gives us a +1, and minus 115/3 gets recorded in the last entry. Now in the second row, our leading entry is 1. That's what we wanted to see. Now we just need to make sure that in the first row, the leading entry is equal to 1. And multiplying worked for the second row. We might try to do the same thing for the first row. Multiply everything in the first row by 1 over 150. And doing that to 150, 150 over 150 equals 1. 150 over 150 gives us another 1. And then 2000 over 150 simplifies to the fraction 40 over 3. And at this point, we have made sure that the leading entries in each row are 1. Now the last thing to check is that each leading 1 is the only non-zero entry in its column. And so we'll take a look at this one, and it is the only non-zero entry. Everything else in that column is 0. In the second row, though, our leading 1 is not the only non-zero entry. I see a 1 above it. And the point is, to be in reduced echelon form, you need to have zeros not only below the leading entries, but also above the leading ones, above the leading entries. So I need in particular to make sure that this 1 gets changed to a 0 through some operation. Now one thing I can do is take that 1 that is in that position, and if I multiply the second row by -1 and add it to row 1 to create our new row 1, in other words, if I do a replacement operation, -0 plus 1 gives us 1, -1 plus +1 gives us a 0, which is what I was hoping for, and then minus -115 over 3 plus 40 over 3 gives us +155 over 3. Now at this point, the matrix is in reduced echelon form because our leading entries have zeros underneath and to the left of them. We also have the leading entries equaling 1. And what's more, what's new for us here is that above the 1s, you should also have zeros as well for those leading entries. And that's what we do see in that first row, second column. Now, after you have gotten your matrix into reduced echelon form, which we now have, step 4 is to write the system of equations corresponding to the reduced echelon form. If I go to this reduced echelon form and I read off the equations that go with each row, I'll see that x1 is equal to 155 over 3, or if we write that in decimal form, we can write it as the repeating decimal 51.6666 ... The second row of the matrix corresponds to the equation x2 is -115 over 3, which if we write that in fraction form, we'll get -38.3333 ... Now, if you remember the problem this came from in our first video, the diet problem, this is the solution that we had identified as working for our problem. So we end up solving the system, finding the solution that we had arrived at in a mysterious way in that first video. All right, now we are going to illustrate with further examples, but I'll just kind of show you again those steps. Step 1 is to write the augmented matrix of the system. Step 2 is to use elementary row operations to put the augmented matrix in echelon form. Pause to see if there happen to be no solutions. If there are solutions, continue to row reduce to obtain the reduced echelon form. And step 4 was to write the system of equations corresponding to the matrix in echelon form. And actually, in the example we just saw, once you write the system of equations, you have the solution. Now, this last step, step 5, will happen when you are dealing with other types of systems. We'll see examples of that in just a few minutes. But we've already seen those first 4 steps illustrated. Let's take another look at another example. And we'll use this to give a bit more illustration to that step 2. So let's start with an example of a system having no solution. Now, you might remember these from the first half of this part B. We had given this as an example of a system having no solution. We can see that graphically because the graphs of these 2 lines are parallel and they don't intersect anywhere, so there's actually not a solution to the system. Now, how would we know that by reducing the matrix? Let's follow the steps. So step 1 is to write the augmented matrix of the system. Step 2 is to use elementary row operations to row reduce your matrix to an echelon form. So what I'll do, because I have a leading entry in that first column, I need to create a 0 underneath it. So I might take -4 times row 1 and add it to row 2 to make my new row 2. So if you can imagine, we might write above here -4 times row 1. -4 times row 1 would look like -4, -8, and positive 24. If I were to add -4 to 4, I'll get 0. Add -8 to positive 8, that gives me 0. Add positive 24 to -48, that's going to give me -24. Okay, now at this point, we put it in echelon form. We should check to see if there might not be solutions. And what we'll see is that if you take a look at that second equation, it's notable because of the zeros it has there. If we think about the equation that goes with this last row, we would read it off as 0x plus 0y equals -24. But 0x plus 0y just equals 0 no matter what x and y are. The left-hand side is 0, the right-hand side is -24. And those two things should not equal each other. We get sort of a nonsensical equation here. And that nonsensical equation cannot be satisfied by any choice of x or y. Now, because there's no solution to this this matrix, this echelon form matrix, that means there should not be a solution to the original system. And that agrees with what we knew before. There's no solution. Okay, so what will happen in general is if you use your elementary row operations, and once your matrix is in echelon form, you see that some row has its leading entry in the last column. Well, having the leading entry in the last column means that the left-hand side of your equation is 0 and the right-hand side is not 0. And that's going to give us a nonsensical equation, and that's going to tell us that there should be no solution. And that's how you'll know. A linear system has a solution if it doesn't have an equation like this. If it does have an equation like this in its echelon form, then there is no solution. While we're in the neighborhood talking about locations of leading entries, let's use some terminology. We'll define a pivot position to be a location that corresponds to a leading entry once the matrix is in echelon form. A pivot column is a column that contains a pivot position. So to illustrate that, let's take a look at a matrix that we've seen before. You might remember from earlier that if we do our elementary row operations on this, one possible echelon form of the matrix looks like this. Now, a pivot position is a location that corresponds to a leading entry of a row in echelon form. So this position that the 1 is in, this position that -2 is in, and this position that 7 is in, these three locations are pivot positions. And pivot columns for the matrix would be column 1, column 2, and column 3, because that's where the pivot positions are located. Now, one thing to be very, very careful about, our textbook and our course will mention pivot positions many times as we go throughout the semester. Pivot positions refer to the locations of the leading entries of the rows in echelon form. So one strange thing you might see is that sometimes linear algebra textbooks talk about the pivot positions of a matrix when the matrix is not in echelon form. And so, for instance, if I were to talk about the pivot positions of the original matrix, I would still refer to those three positions as the pivot positions, even though these aren't necessarily the locations of leading entries. In the second row and the third row, for instance, your leading entries lie somewhere else. What we're saying when we call these the pivot positions is that if you were to put it in echelon form, that's where the leading entries would lie. So we call these the pivot positions even though it's not in echelon form, just keeping an eye on what the echelon form would look like if we put it there. For this reason, I like to think of pivot positions and pivot columns as being like the studs in a house. Like when you frame a wall, when you build a house, you put up these vertical pieces of wood, and you know that once the house is finished, you're not going to see these things. They're going to be covered with sheetrock. There may be insulation placed between some of these. They're not going to be very apparent when you see the finished house. But if you were to have occasion to rip out a wall in your house, once you take down the sheetrock, you'll see these studs. And in that way, I like to think of this, there may be other entries kind of clouding things up, but when you reveal the pivot positions by putting the matrix in echelon form, like tearing out a wall, you'll see that these are sort of forming kind of a skeleton of your matrix in the same way the framing forms a skeleton of your house in some sense. All right, so what we had just got done saying is if you want to see if there are solutions or not to your system, once it's in echelon form, you should see if there's a leading entry in the last column. Another way to say that is a linear system has no solution exactly when in echelon form of the augmented matrix there is a pivot position in the last column. If the last column is a pivot column, then that means that there will be an equation where 0 is equal to something that's not 0. You'll end up having a nonsensical equation, which means there's no solution. Okay, so that's a little bit more detail on what you should look for to pause to see if there are no solutions. You want to look to see if there's a pivot position in the last column. If there is, that means there's no solutions. You should stop at step 2. If you don't see a pivot position in the last column, then you're going to go ahead and carry on with the later steps of our technique. All right, we need to see more examples. In particular, let's have an example that leads us to describe exactly what's going on in step 5. So we will take a look at the example we had seen in our very first video. We've got electric current going through a circuit, and we want to identify how much current is flowing through each segment in this circuit. Now, using Kirchhoff's laws back in the first video, we had written down a system of equations to kind of model the flow in and the flow out of current at each point in our network. And we had even in that first video identified, just by presenting it to you, we'd identified a number of different solutions. Each one of these is a valid setting for x1, x2, x3, x4, x5 that makes the system of equations true. And that last one is notable because you can choose x3 and x5 to be anything, and as long as you figure out what x1 is based on your choices of x3 and x5, and do the same for x2 and x4, you'll see that the equations are all satisfied. Whatever you get for x1 and x2, you add them together and you do get 10, and the second equation and third and fourth equations are also satisfied as well. So this system actually ended up having multiple solutions, actually infinitely many, because of the infinitely many different ways you could choose x3 and x5 to be real numbers. So let's take a look at our technique and see how it might happen that we end up with more than one solution. What does that look like in practice? So we're going to take the augmented matrix of the system we had just seen, filling in the zeros in the missing spots, and recording the coefficients on the right-hand sides. We get this as our augmented matrix. Remember, step 2 was to use elementary row operations to put that matrix in echelon form. That means I need to get a 0 underneath this leading entry. So I'm going to take -1 times row 1 and add that to row 3. So putting -1 in through the first row, we'd get a -1, -1, 0, 0, 0, -10, and adding those entries to the corresponding entries in the row 3, -1 plus 1 gives us 0, -1 plus 0 gives us -1, -0 plus 1 gives us 1, -0 plus 0 is 0, -0 plus -1 is -1, and -10 plus 0 gives us -10. So our new row 3 is the old row 3 plus -1 times row 1. Okay, at that point, we've gotten the 0 in the first column where we wanted it. So the leading entry all has only zeros underneath it. At this point, though, we've kind of messed up our second column. Now our leading entry coming from the second row has a non-zero entry underneath it. We need to fix that. So what we'll do is we'll take the second row and we'll add it to the third row, and that will create a 0 in that spot. We'll add 0 plus 0, 1 plus -1, -1 plus 1, -1 plus 0, 0 plus -1, and 0 plus -10. Record the answers in our new row 3, and that's what it looks like. One thing to be careful of, one thing to mention, when you saw that -1 there and you knew that it needed to be a 0, some of you may have been tempted to use the 1 in the first row to create a 0 there, and it would be a valid elementary row operation to add row 1 to row 3. If you did that, though, you would get a 1 plus a -1 creating a 0 in that second entry, but pay attention to the first column. Taking the first row's 1 and adding it to the 0 there would create a 1 in the first column, and we don't want to have a 1 underneath the first row. So in particular, as you are creating zeros in this step, you want to make sure that the rows you choose to do your replacing, the rows you use to add a multiple to your row, you want to choose a row that starts off with a bunch of zeros. I need to use the fact that this is a 0 in order to not mess up the 0 that I had before. So that's why I chose row 2 rather than row 1 in choosing to replace row 3. Now, once we're here, again, we're not quite done because this -1 is a leading entry and it doesn't have a 0 underneath it, and we need that for echelon form. So -1 plus 1 is just equal to 0, so maybe what I'll do is just take row 3 plus row 4 to create the row 4. And again, I'm using row 3 in particular because it's got a bunch of zeros which are not going to mess with the zeros already present in row 4. And once I do add negative row 3, or a positive, sorry, big row 3 times 1 and add it to row 4 and record the answer in row 4, it actually ends up giving me a 0 in every single entry. Now that's okay actually, because that row of zeros is in the last row, which is what should happen if it's in echelon form. If that didn't happen, if the row of zeros were elsewhere, we could just sort of interchange rows until we move the row of zeros to the bottom. We do have the leading entries appearing from moving from left to right as we go down the rows, and the leading entries all have zeros underneath them, so this matrix is in echelon form. Now we're going to pause to see if there are no solutions to this. What we're checking for is to see where the pivot positions are. So pivot position here, pivot position here, pivot position here, and there is no pivot position in the last row because it's a row of zeros. So what we did not see was a pivot position in the last column, and that tells us that yes, indeed, there are solutions to this system of equations. Again, since there is no pivot position in the last column, there is at least one solution to the system of equations. All right, now this matrix is in echelon form, but it's not in reduced echelon form. Remember, what we need to have for reduced echelon form is that we want to see zeros not only below but also above those leading entries. So I'll need to get rid of that 1 and make it a 0 somehow, get rid of that -1 and make it a 0 as well. And we do that through elementary row operations. So moving from the bottom to the top, we can actually do this in any way we want to get a positive 1 in row 3 as a leading entry, because that's also a requirement for reduced echelon form. I'm going to go ahead and multiply that third row through by -1. The zeros will stay zeros, the minuses will become positive ones, and I do have 1 as a leading entry in every row of the matrix so far, so this is good. Now I'll go ahead and try to create those zeros. Taking a look at row 3, I might use the fact that these are all zeros here, and that's a positive 1. I'll add that to the row above it to create a 0 in that spot, and without changing the location of a leading entry or anything earlier. So adding minus row 3 to row, adding row 3 to row 2 gives us this result. Then, taking a look at the pivot position here in the second row, I need a 0 above it. So I'm going to take -1 times row 2 and add that to row 1. And when I do that, I'm going to end up with a 1, 0, 1, 0, -1, 10 as the entries in my new version of row 1. At this point, we have gone ahead and put our matrix in reduced echelon form. So that's the first 3 steps of our technique. Let's take a look at those steps again. After you've done those first 3 steps, you want to write the system of equations corresponding to the matrix in the reduced echelon form you just came up with. And then in step 5, you're supposed to rewrite those equations in terms of basic variables and free variables. So let's go ahead and see what that looks like here. If I were to write these equations in step 4 in terms of just equations, if I were to read that first row of the matrix, I would see x1, 1x1 rather, plus x3 minus x5 is equal to 10. And I would see x2 minus x3 plus x5 plus x5 is equal to 0. And x4 plus x5 is equal to 0. Now, what you'll notice here is that we are going to define variables as being of one of 2 types, basic variables or free variables. And the difference is where the variables first appear. So a basic variable is one corresponding to a pivot position. So these variables that correspond to the leading entries in the rows, so x1, x2, and x4 each have a pivot position corresponding to that variable. Another way to say that is to say that the first column, the second, and the fourth column are the pivot columns, and that means that x1, x2, x4 are the basic variables. Now, there is no pivot position in column 3 or column 5, and that means that x3 and x5 don't correspond to a pivot position. What we'll say is instead that these are free variables. So x3 and x5 are free variables, and as we're told here, we're going to write a line for each basic or free variable. I'm going to write a line for x1, and what I'll do to get that line is I'll take the equation that x1 was the pivot variable in, x1 plus x3 minus x5 is equal to 10, and I will solve that equation for x1. We'll get that x1 is equal to 10 minus x3 plus x5. The next basic variable is x2, and if I solve that second row's equation for x2, I'll get that x2 is equal to positive 1 x3 minus x5. And likewise, x4, our last basic variable, corresponds to the equation x4 equals minus x5. To write my answer, I'm going to write each of these equations for x1, x2, and x4, just as they're solved for up there. And then for x3 and for x5, these free variables, I'm going to write the phrase x3 is free and write x5 is free. All right? Now, when you have done that, you have satisfied the step 5. We write each basic variable in terms of any free variables, and we say that the non-basic variables are free. In other words, we've got these lines saying that x3 and x5 are free. Now, at this stage, I want to point out that there's a special name for this kind of solution. This is called a parametric form of the solution, and the reason why has everything to do with these free variables. The fact that x3 and x5 are free mean that they can take on different values and we can still get a solution. That means that x3 and x5 are what we call parameters. And because they're parameters and choosing different values for those parameters will change the rest of your solution, we'll call this a parametric description of our solution. All right? Okay, with that, we have solved the system. And when you do end up with free variables, it is always the case that you will have infinitely many solutions just because there are infinitely many choices for those free variables. Now, for this last example, I'm actually going to leave it to you. This was from our first video, the problem of balancing a chemical equation by determining how many of each molecule needed to show up on either side. We won't go into the details of how we set up the system of equations. You can go back to part A if you wanted to review that process. But here is our system of equations that we came up with here for our problem of the combustion of propane. If we write the augmented matrix that goes with this system, we end up with this matrix here. Now, in that first video, we showed you a solution, and we actually said that there are infinitely many solutions because you can choose x4 to be any integer you like and figure out what x1 and x2 and x3 are. What we'll point out here is that x1, x2, x3, and x4 written in this way, this is a parametric description of the solution, and there are infinitely many solutions to this. What I'd like to challenge you to do, though, is to follow the steps we've outlined, the steps from section 1.2, these steps involving elementary row operations on the augmented matrix, and see if you can figure out where this parametric solution comes from. What does the matrix do along the way, and where do you end up with that will eventually lead you to writing out your solution in this form? See if you can arrive at this on your own. And good luck to you. Please let me know if you have any questions as you do that. But with that, we'll go back to our outcomes. We'll mention first the big questions. At this point in part 1 and part 2 of this part B, we have talked about how to solve any linear system and how to describe the solution set. Even if there are infinitely many answers, we can describe the complete solution set by giving a parametric description, as we talked about, with free variables and basic variables. We have seen examples where you might have no solution or one solution or infinitely many solutions to a linear system. In the next video, in part C, we're going to talk about whether other possibilities are available, whether you can have a linear system with exactly 3 solutions or something different. We'll talk about that. And then in later videos in chapter 1, we'll talk about other perspectives from which we can take a look at these problems and their solutions. With that, we'll take another quick look at the outcomes. Hopefully you are able to define all of these terms. This was a very, very vocabulary intensive part of chapter 1, so please do make sure that you are able to use this vocabulary. Your life will be very, very much easier if you are able to use these phrases in sentences and know what they mean. Please also be sure, before you leave these 2 videos in part B, be sure to be able to determine whether a given matrix is in echelon form or reduced echelon form, and be sure to know how to perform row operations to transform a given matrix into echelon form or a given matrix into reduced echelon form. Please review that if you need to. Finally, you want to be able to locate the pivot positions and pivot columns of a given matrix. I'll remind you as a hint that you need to put your matrix in echelon form before you identify where those are, and use this information to determine which of the variables of the corresponding linear system is a basic variable and which is a free variable. And then using basic and free variables, give a parametric description of the solution set of a linear system. Well, with that, we'll wrap up things here. If you have any questions, please let me know. Otherwise, I'll see you in the next video. Until then.